So hello everyone and welcome back to this next video in the DC-DC video series. So this is where we had left off in the previous lecture, where we had run the simulation of the transformer and we had verified the result. So we had a few problems, a few bugs, and there was an instability problem. So we had solved both of them. So as you can see, there is a half cycle or almost one cycle of transient. This transient was initially blowing up, and with some changes, particularly the changes to the model of the winding, we were able to suppress these transients until it became a steady waveform. So now, because we have a 1:1 transformer, both voltages, that is the winding voltage of the primary and the secondary, are exactly the same. Now in this video, we are going to start playing around with the winding ratio and look at how these voltages and currents differ. So let's go back to the simulator. And as always, before I start this video, a little bit of background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length video courses on the MOOC website Udemy. So the first one is simulating power electronic circuits using Python. And in this, I talk about the basics of how you can use Python, how you can install Python and Python power electronics, some basics of power electronics, and finally a case study of how can you simulate a buck converter. Then if you are interested more on the digital signal processing or the control side, I have another course which is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about some basic theory with respect to signal processing. And finally, there is a case study of how to design and implement a low pass filter and notch filter. And design happens using frequency response characteristics using Python packages. And finally, and this is very relevant to the next few lectures, the last few lectures we've been that is simulation of magnetics for power electronics using Python. And in this I talk about the basics of magnetism, especially related to electrical engineering, how you can model an inductor, a coupled inductor, and a transformer. And finally I have one case study in which I simulate a flyback converter. So these three courses are relevant if you are interested in something a little more comprehensive to learn power electronics and electrical engineering in general. The links for these courses are provided in the description of this video. So let me return back to my the actual simulator. So this is where we had left off. We had plotted the winding voltages. Let me go over to the code and let me close this as well. So this is where we were. So this is the model of the transformer, basically a control file. So as I said, we had kept the rating of the two voltages, or rather the voltage rating of the two windings, to be the same, right? And we had chosen 240 volts. So now that we have at least a basic transformer working, let's start playing around with it. So let us have a step up voltage, or rather let's do a step down, because we have 240 volts on the primary side. So like if you go back to the transformer circuit, our voltage source is 240 volts and we are applying 240 volts to winding 1. So let's keep winding 1 voltage rating to be 240 volts. Let's change winding 2 to be 120 volts. So we have a step down transformer, right? So let me go and change this. So with this change, what else do we need to do? We don't have to change anything else, right? For example, if you look at VA rated is the same because this is the volt ampere rating of the transformer. Now, this would change depending upon the winding ratios. For example, if I were to have, let's say, a 240 by 12 volt transformer, you can't now use a 10,000 VA rating. Simple reason, because a 240 volt by 12 volt transformer is usually a signal transformer, right? And that usually has a rating of maybe just 1 amp or so. So you would want to change this to around 250 VA, right? Similarly, if you had a step up, so for example, if it was, let's say, 240 volts to 11 kV, in that case, you don't want a 10,000 VA transformer either. You would want something a little bigger, maybe 100,000 or maybe 50,000, something like that, right? Because now this is a major step up transformer that probably feeds an entire house or a set of houses, right? Now the rest does not have to change frequency, rating, everything else. And at the same time, let me just delete this because we don't need this print anymore. And at the same time, we do not need to change anything else as all of them are being calculated, right? So with this change, let me go over and run the simulation again. So if we go and click on the run button, it says simulation is running. Let's go to the command line. There is no error, so we are good to go, right? So let's go back and let's plot the winding voltages. And we have instability, right? The same thing, we have instability all over again. Now, these instability problems can be a little difficult to solve, but like I said, one simple way to do this is just to go and increase your resistance just a little, right? So I would just go and increase this to 100. And let's run the simulation again. Let's check, there is no error. And let's plot it. And now it's working. So, like I said, there is this playing around with winding resistance, or rather the resistance of the model is a little tricky, and this is something that appears in any custom model that we develop, right? Even if we go on to develop an induction motor model or a synchronous motor model, almost all of them are voltage sources in series with impedance. Eventually that is how it is. It's Thevenin equivalent. For example, either you can come up with a Thevenin's equivalent or a Norton's equivalent, right? Thevenin's equivalent means a voltage source in series with a resistance, or Norton's equivalent is a current source in parallel with a resistance. So this resistance to the winding, you need to be able to take into consideration that this resistance has to be big enough that if this transformer was not energized from both terminals, or let's say it was energized only from one terminal, in that case the current should not have large spikes. Okay? This is something that you gain mainly from experience. Another way of actually decreasing the possibility of instability is to decrease the time step. But decreasing the time step usually prolongs your simulation. It just takes more time to simulate. So let me just go and close this. Right. So the simulation is running, but as you can see, there is one huge glaring mistake, and that is we wanted a step down transformer, right? So therefore we do expect V2 to be much smaller than V1. That's not however happening. So let's go and have a look. So as before, when we do come up with an error in our simulation, the first thing you should always do is let's review our control code, right? So let's have a look at what we've done. As we've done, all this is pretty much the same. So I guess this can be changed for now. We can actually update this a little later, but for now let it be. We have changed these voltage ratings, right? So we made one to be half the other. That's all right. We set a VA rating, which is also all right. We calculate the current rating for both windings. We come here, we calculate the self-inductances, and we calculate the leakage inductance, and we are calculating the magnetizing inductance, right? Finally, we are setting the resistance of the model. So these calculations seem correct, and also our implementation is okay. So let us check if there is a conceptual mistake. The problem is there is a conceptual mistake. If you look at what we have done here, this is what is our concept. We are calculating the induced EMF from the applied voltage, that is all the way up here, right? From the applied voltage with respect to the resistive drop. After which we are now integrating this induced EMF to calculate the flux linkages. Now, it's important to understand the flux linkages. How are the flux linkages actually associated? The flux linkage of every winding is the self-inductance of the winding multiplied by the current in the winding and the sum of the mutual inductance of any other winding and the current through the winding. It's very important to understand. It is the mutual inductance, right? It is not the magnetizing inductance. Now let's come over here and see what we've done. What we have done here is we have taken the self-inductance, multiplied it by the current of the winding. This is perfectly okay. It is this calculation which is not correct. We are multiplying the magnetizing inductance of the winding with respect to the current of the winding. This is not what we should be doing. We have to multiply this with the mutual inductance of this winding with respect to, we have to take into consideration the mutual inductance. So now what is mutual inductance? Now let's come all the way here and let's calculate mutual inductance. We have already calculated the winding inductance. So let's put another comment and call this mutual inductance. Now mutual inductance, let's call it M12, is usually the square root 2. So let's say, for example, I can just say square root of the two inductances, right? So we have to now calculate LM1 multiplied by LM2, right? Now this goes from the basic definition of a mutual inductance. Let me write that here. It is M is equal to, there is a K term, K is the coupling factor, square root 2 of L1 multiplied by L2. So the mutual inductance between any two inductances with inductance L1 and inductance L2 can be written as the square root of the two inductances multiplied by a coupling factor. What is this coupling factor? This is the amount of magnetic flux that links one inductor with the other, right? Because in any coupled inductors, there will never be 100% linkage. There will be always some amount of leakage. The reason why we have not considered this in this equation is because we are already calculating the leakage. We are already taking a 1% leakage in both windings. So therefore, we are taking into account this coupling factor already. There is no need to take into account again. It is this mutual inductance that we now have to include in our equations. So let's go back here and let's do this, write this again. I'm going to write these two, that is psi 1 is equal to L1 multiplied by I1 plus M12 into I2, and here psi I2 into I2 plus M12 into I1, right? So here the mutual inductance, right? You could write it, actually speaking, you could write this as M12 and M21 to be more precise, but it doesn't really matter that much, because if you have two inductances, the mutual inductance of one with respect to the other will be the same. It's reciprocal, right? So therefore, we don't have to take that into account. So what does this actually mean? What this means is this current here is not just impacted by the magnetizing inductance of that winding, but is the mutual inductance. This takes into account the mutual inductance. This is therefore what we should be doing. So let us replace LM1 by M12 right, and let us run this simulation. So we have to stop it first and let's run it again. Let's go back to the command line. Yes, it is running, and let's click on the run plot button. And now we do have that result, right? Now I'm just going to plot once more so that we have a few more cycles. And yes, we do. So if you have a look here, now you see the blue line is the primary voltage, or rather the winding 1. This winding 1 is supplied by a 240 volt voltage source. The orange line or the yellow line is winding 2 voltage, and this winding 2 voltage is now half the voltage of the primary winding, right? And this is expected. The reason because we have used a 2:1 ratio for our transformer. Our winding 1 voltage is 240 volts, winding 2 voltage rating is 120 volts. So we have a 2:1 step down transformer, and that's exactly what we see here, right? Now I'm going to stop this lecture because it's getting a little long. In the next lecture we will continue with this, have another look at it, and also look at the currents. So as before, if you have any doubts, please do post in the comments, or send me an email, or message me on social media, whichever is your preference, or I will see you next week where we will continue with this. So thank you so much for watching, and see you soon. Goodbye for now.